Welcome to the fourth Heat and Materials lecture. In the last lecture I introduced convection and Newton's law of cooling, the convective heat transfer coefficient H. Then I introduced the basics of black body radiation, and then I introduced the basics of radiative heat transfer in terms of black body radiation and emissivity, so to account for the fact that real bodies are not black bodies. And I then defined a strongly temperature dependent radiative heat transfer coefficient, and I used these heat transfer coefficients to basically expand the one-dimensional thermal resistance model to include convection and radiation. And then I left you with a final problem to assess the fraction of energy lost by convection and by radiation in the case of a particular piece of steel. Before I look at the answer to that problem, the outline for this session is to otherwise look at expanding the thermal resistance model to include cylindrical coordinates, and then moving on to look at a time-dependent problem related to the solidification of metal in a sand mould. And this is where, in terms of spatial dimensions, I deal with a one-dimensional heat conduction equation, but I actually also introduce time dependence, and then I look at a particular special case, the semi-infinite solution. So first of all, the calculation from last time, where you were asked to consider a piece of steel with an emissivity of 0.1 in a large room at 10 Celsius with a convective heat transfer coefficient of 8 watts per meter squared per Kelvin, and you were asked to essentially assess the fraction of heat lost by radiation and that lost by convection for the steel at two different temperatures. To get an answer, you need to use this radiative heat transfer coefficient, remembering it is strongly temperature dependent, and also remembering to convert all of your temperatures to Kelvin. So for the 1000 degrees centigrade case, this means our relevant temperatures are actually given as. So for the 1000 degrees Celsius case, this means the relevant temperatures are 1273 Kelvin and 283 Kelvin, and that's what I've included in this calculation here. It gives us a radiative heat transfer coefficient of 15, strictly watts per meter squared per Kelvin. Therefore, the fraction of energy lost by convection is given by 8 divided by the sum of 8 plus 15, which gives us an overall fraction of 0.35. The fraction lost by radiation is obviously just 1 minus that, or 0.65. For the 200 degrees centigrade case, the corresponding fractions are 0.86 and 0.14 respectively. I now want to move on to consider the case of heat transfer from a pipe, in other words a cylindrical geometry. So what is the outer surface temperature of a pipe carrying a hot or cold fluid at a known temperature, and correspondingly therefore how much heat can be gained or lost from that fluid? So the interior temperature of this pipe I call T1, and the exterior temperature will be T2. Now if I assume that my pipe is very long, I can get away with ignoring variations of temperature along the length, although obviously in a real system you would need some way of actually maintaining the temperature inside the pipe if heat is being lost from the walls of the pipe. In terms of geometry, it is natural to use cylindrical polar coordinates r, theta, z, and I'm going to assume that the system is circularly symmetric, so there are no variations in temperature with theta. This means the top and the bottom of the pipe will be the same temperature, which might well not be true in a real system. But it does mean that I can therefore treat the problem as one-dimensional. All the temperature variation is in a radial direction, so I can recast Fourier's law as Q equals minus Ka dt by dr. You'll notice that that looks like I've just simply replaced x by r in Fourier's law. Strictly, the conversion from Cartesian to cylindrical polar coordinates involves a little bit more work than that. It just so happens that for this simple one-dimensional case, it looks like I've simply replaced x by r. The big difference is that A now depends on the radial distance from the centre of the pipe, because the surface area of a cylinder is always given by the circumference of the cylinder times the length. Now the length I've just said is going to be very long, but it is good practice to leave it in explicitly, and the circumference obviously is 2 pi r. This means that when we come to try and solve this problem, we are now integrating between our inner and outer radius of the pipe, and integrating between the inner and outer temperatures, which are T1 and T2. But of course the term in A has a dependence on R. So now when I bring all my terms into R onto the left hand side and all my terms into the right hand side, I have effectively inside my integral dr over r. The other terms in that integral are constant q over 2 pi L. We are assuming a fixed heat flow and a defined length of pipe, and we're integrating between the inner radius, which is R1, and the outer radius, which is R2. And on the other side, we're integrating between T1 and T2, and as before, strictly the thermal conductivity could vary with temperature. However, we will assume that as before we can define a mean thermal conductivity, and that's what I've done in going to the next line. On the left hand side, of course, the integral of dr over r integrates to log of r, and when you apply the limits, this gives you log of r2 over r1. Rearranging that equation gives me this expression for q, and once again I can draw a parallel with Ohm's law, where the heat flow is equal to the current I, temperature difference is equivalent to the potential difference of voltage, and the thermal resistance is now given by this expression at the bottom of the slide, and you'll see that it involves the log of the ratio of R2 over R1 rather than a linear difference in position. Now this leads to some subtle effects. If we now consider the case of a tube furnace, where we have initially a system that has convection inside and out. Convection inside is convective heat transfer coefficient of HI, an interior temperature T inside, and a convective heat transfer coefficient of HO outside and a corresponding temperature T outside. The thermal resistance in this particular case will be given by two terms that relate to convection, and note of course the convective terms are both of the form 1 over HA, but A is of course 2 pi appropriate radius, in this case because it's the inner one is R1, times L. And then the term for the wall of the furnace is this log R2 over R1 divided by 2 pi K1L. If we now add insulation to the outside of this tube furnace, we of course increase the outer radius. So the outer convective term now involves R3 rather than R2, and we've also added in this additional term related to the thermal conductivity of the insulation, as well as the ratio of the outer radius to the inner radius of the insulating layer. I can compare those two equations and say that R after, so R with the insulation, equals the initial case plus this term which related to the inner and outer radius of the insulating layer, plus the convective term that related to the outside, minus the convective term that was initially present on the initial resistance. Delta R is then just the difference between these two equations, and I've normalized it very slightly. I've then plotted in the graph below delta R versus the radius ratio R3 over R2. Now the interesting thing about this result is you see that some of these results are actually negative, and that implies that insulation actually increases the heat loss. This counterintuitive result is actually logical, because what is happening is that the overall increase in surface area, and therefore the overall increase in convective loss, is actually greater than the reduction in heat loss by putting in a layer of low thermal conductivity. It only applies in some cases. You'll see there are plenty of these solutions that are positive, so insulation does as you expect, but there are some cases where it is negative. This means that overall there is a critical radius of insulation, and you need to basically add more than this for insulation to have a benefit. We can obtain that by taking the R after resistance, differentiating that with respect to R3 and setting the result to 0. Most of the terms then cancel out, and we get a very simple result that the critical radius of insulation equals the ratio of the thermal conductivity of the insulating layer to the convective heat transfer coefficient outside of the furnace. Now if we take the thermal conductivity of the insulating layer to be that of rock wool, which is 0.04, a reasonable value for free convection of air, which is 8 watts per meter squared per Kelvin, we end up with a value of R3 equals 0.005 meters, or in other words 5 millimeters. This result is only really going to be important for dealing with small pipes and with current carrying wires, but under those circumstances it is possible that adding insulation would actually increase heat loss rather than decrease it. Finally, there is one thing to particularly point out, is that although you can apply this approach to looking at the insulation on the current carrying wires, you'd have to be careful about thinking about what was happening inside the wire, because you can't strictly use the approach for solid cylinders. Simple reason for that is that would require an inner radius of R equals 0, and log of 0 is ill-defined.